Okay, so very good morning to all of you, and we'll be talking about spin, and we will extend our discussion to spinors. And I think this discussion should conclude when we will talk about the Pauli's spin matrices, right? So we have two models for the spin of the microscopic particles. Now, we have a classical spin and we have the quantum mechanical spin. And classical spin is purely intuitive. You can feel it, you can realize it. You have a body, and this body has an axis of rotation. So if there is a body, a classical body, it has axis of rotation. This rotation with respect to the axis of this body is what is called as the spin motion. And when we say it has a spin motion, it has spin angular momentum. And using the concept of spin in classical domain, we can calculate various physical quantities. We can calculate moment of inertia. We can calculate the center of mass of that body, keeping in view the spin of this classical object. But when we make a transition to the microscopic world, now what is our microscopic world? It's a world filled with particles. And these particles are they're atoms, they're molecules, they are protons, they're neutrons, they're electrons, and all other elementary particles. You don't have a description, you don't have a physicality in microscopic world. You have something what's called as degree of freedom. The spin is basically degree of freedom that's associated with these microscopic particles. And we have the confirmation of existence of spin using the well-known experiment what's called as Stern-Gerlach experiment. If you rightly remember that experiment, you have neutral charged silver atoms, you allow them to pass through an inhomogeneous magnetic field. Then what you see is that you have two spots on the screen, and these two spots lead us to predict that these microscopic particles have spin associated with them, right? Now, if I rightly go back to your semester first, you have gone through solving Schrodinger's equation on hydrogen atom, and you go through all that mathematical process, okay, and you have three general equations which you separate out, and you separate out these equations using some constants. And if you go back to that angular part of Schrodinger's equation, that leads to the quantization of angular momentum. And that angular momentum is given in terms of angular momentum quantum numbers. Capital L is under root of s times s plus 1 h bar, right? So when you have an experimental confirmation of existence of spin, you must have at the same time the prediction of that spin. So if we will go on the same lines of spin, we can think about the quantization of this spin also in the quantum world, which is not probably coming as the solution to the Schrodinger's equation, because spin is something that doesn't come naturally by solving the Schrodinger's equation for hydrogen atom. But we can put an analogy, and using that analogy, we can say that spin angular momentum, it should also be quantized, and this spin angular momentum must be equal to under root of s into s plus 1 h. So, since we are moving on on learning this advanced nature of spin, let me introduce you with the problem. Let me introduce you with what we have. We have some background of this situation that we are going to talk about. And if anybody has questions, you can ask me the questions, right? So electron spin, it's a very fundamental property. It's a very basic property of the electrons. It's an intrinsic thing. It's not something that we talk about the classical objects. For classical objects, you have a pure geometrical interpretation of the spin, right? But here, it is something, but at the same time, it's an intrinsic property of these particles. It's an intrinsic property. It is there. But what's the nature of this intrinsic property? We cannot give any physicality to that. So, it was discovered through Stern-Gerlach experiment. I talked about it, and it's not your classical spinning, but a quantum degree of freedom. So if you have to answer what is a quantum mechanical spin, you will say, come on, it's a degree of freedom that's associated with these quantum mechanical particles. And you have these numbers linked with the spin angular momentum, and that's plus half. And plus half tells us that the spin is up, and the minus half tells us that the spin is down. This is not that physical up and down. You have to keep this thing in your mind. It's wrong to feel that way. We will see it later on. So spin it's quantum mechanical in nature. It's governed by the laws of quantum mechanics, right? And the spin it's represented by the term that's called as spinors. And the advancement of these spinors leads to your big branches like particle physics. Spinors have a very, very beautiful role in discussing the particle physics and quantum computers. So what they require a complex vector space. When you have to interpret them, you have to interpret them mathematically. There's no physicality involved here. It's all mathematical framework. So observable only through the magnetic moment. Spin is there. The electron has a spin, but you cannot measure it unless you will make it interact with an external disturbance. It will show you the spin. It will show the existence of spin when you will allow it to interact with an external magnetic moment. So external magnetic moment means magnetic field. Okay, so interactions with the field. So you can sense the spin of the particles through the interaction that you have. So what we have to have a mathematical representation of spin, and these spin states, they are represented by two component spinors. Now what is a spinor? It's a two-dimensional vector space. A spinor is a two-dimensional vector space. So these things, the spin up and spin down, it is in the form of rho, but this is not the actual representation that I will choose. I will be choosing a column vector for spin up and spin down, so we'll discuss it. And what's happening? Operators for the measurement along x, y, and z axis are your Pauli matrices. So what you have these spinors, and what you do, you operate these spinors using Pauli's matrices. And Pauli's matrices are what? They are what? They are operators. Okay? They are operators. They are operators in the form of matrices. They act on your spinors, and they give you a transition. They give you the transformation of the spin. They tell you how the spin makes the transition from one state to another state. Okay, so this is okay, fine. Okay, this is done. Come on. Okay, they are a theoretical construct. They are here, they are in our brain. We design them, we prepare them, we make their mathematical format, and they are not the physical particles. So when we talk about the spinors, they are not the physical particles, but mathematical tools, the mathematical tools that you exert to see how the dynamics of the spins take place. They are analogs to how the virtual particles, if you have to talk about the vacuum using Feynman diagrams, what happens is you have constantly manufacturing of the particles. You have particles, antiparticles, particles, antiparticles. But the time scale is very low when you use Heisenberg's uncertainty principle. You cannot sense them, but they are there. So in the same way, we are trying to treat the spin. So this is an example. So what they represent different spin alignments and transformations. So when you make that action, what I said, you use an operator on these spinors, then you see what kind of transformations are there. Now what's their role? Spinors serve as intermediaries in understanding the spin interactions. It tells us how spin interacts. One spin interacts with another spin. How they correlate. And they certainly help us visualize the transition, as I said, the transition of the spin states. They are a basic aid in quantum computers. Now, you must have heard that we have quantum computers. One is at IBM and another is somewhere in China. And they are trying to build this quantum computer. If you talk about a computer, what's a computer? A computer that we use in our laboratories, it works on what? It works on two states, zeros and ones. You have only two states that you can work on and off, right, wrong, good, bad. But in quantum computer, you can work in a state of quantum mechanical superposition. And you have a range of states between 0 and 1. If you remember, in classical computer we have bits, but here we have quantum bits. And these quantum bits can be atoms, they can be electrons, they can be the spin of the electrons, they can be photons. So you can see that what's the length of this subject that you are trying to understand. So we have Pauli Spin matrices, we'll be talking about them in detail, and there is a close relation between spinors and Pauli matrices. As I said, the Pauli matrices, what they do is they flip your spinors. You remember the classical computers? Gates, AND gate, OR gate. These are classical gates. These are weak gates. But here, you can design quantum mechanical gates using the spin of the particles, right? And the basis of the quantum gates is Pauli's spin matrices. You can design the quantum mechanical gates. There are 3 Pauli's spin matrices. If we think in the framework, what sigma x does, it flips the spin of the particle. What sigma y does, it introduces the phase change of the spin. And sigma z, it distinguishes between the spin up state and spin down state. So certainly these spinors can be very useful. You can go in research in the same field. It can be a research field for you where you can work on quantum computer. And spinors will play a very good role, and your Pauli's matrices will certainly be a strong tool to design the gates that work in quantum computers. So how can we visualize these spinors? They can be visualized on a block of sphere. Okay, we'll not go into the details of that, and we will not touch this slide. And talking about its applications. Now you see, this quantum information, right? What we have to discuss the spin, we have to discuss the spinors. We will talk about the Pauli's matrices, and these Pauli's matrices will act on your spinors, and you will have the transitions. But what are the actual applications of these things? The very first thing is the quantum cryptography. Now see, the data that we have, we have phones, we exchange data. This is all working in the domain of classical physics. Our phones are filled with classical physics only. And the data that we have, this data can be, if you have some classified data, this data can be hacked. But that's not the case when you will have quantum mechanical encryption. Because when we fall in the domain of quantum mechanics, what we have two particles, say particle 1 and particle 2. And we bring another particle, say particle 3. The particle 3 can interact with particle 1 and particle 2. Okay? Now particle 1 is at one infinity, particle 2 is at another infinity. There's something called quantum mechanical entanglement. Right? So the two particles, when entangled, they can make an action at very, very large distances. So if somebody is trying to hack your information, the moment he will try, the code that was generated between A and B, this code will be distorted. As an example, I'm trying to just give you an example. So this quantum spin has very strong implications in the world order. If you have a quantum computer, you can purely save your data. And in addition of that, you can break any kind of classical information in the world. Anybody who has a quantum computer in full action will be the king of the world, because they will be able to access everything in the world. So that is where it gives its importance in quantum cryptography. And then there is another important thing, teleportation. So teleportations, you might have an idea that you can teleport a body without teleporting the material. You can teleport this body to another state using what's called as quantum entanglement. And then you have the gates that I talked about. So talking about the experimental basis again here, what we have, this is the last one. Though spinors are theoretical, okay, their behavior matches quantum prediction. It is purely, see, you can design anything in your life, but that doesn't mean everything that you are designing has an implication in reality. But here, you are designing it mathematically, and it has the practical applications, right? Okay, so Stern-Galop experiment, okay, this is the confirmation of existence of the spin of these microscopic particles. ESR and NMR. Come on, can you tell me what's ESR? ESR. What's the full form of ESR? It's also called as, in the physics domain, it's also called as EPR. Oh, come on, don't tell me the name of that paper. Einstein, Podolsky, and Roseman. No, EPR is electron paramagnetic resonance. Okay? You may also call it electron spin resonance. These are the realities. What we do there, we have that, what's called, through which we can see the whole body, apart from CT scan. What is that? MRI. MRI works on the principle of nuclear magnetic resistance. So spin is a reality. It's out there in the market and people are working on it. Okay? So Pauli's matrices, they are verified through the quantum measurements. We can use these Pauli's matrices and we can do some logical calculations using quantum computers. And it has been seen that the power of solving a problem by a quantum computer, there is no match. There's no match between a quantum computer and the classical computer. Okay, so why use seminars? They simplify our abstract spin algebra. Okay, so we come up with that. They're useful in visualizing, helps bridge concepts from quantum theory to computation. I have to go this way. They have limitations, and they are not the real particles for us. Okay? They are not the real particles when you track them, when you write them on your copies. They are just abstract mathematical things that you are doing. They are only meaningful within the defined quantum formalism. They're not everywhere. They are well there in your formalism that you have developed, and should be used carefully in theoretical concepts. So, to conclude this introduction, I was just introducing you with seminars and the Pauli's spin matrices, and this is the conclusion. Spin is a foundation. It's a foundational quantum property. Okay, it's a quantum mechanical property at the microscopic level, and it has very range of implications. Seminars, they offer an imaginative. So this is all going into your brain. Okay, imaginative and practical tool to explore the spin phenomena, how spin is going on, how it's acting, how it's performing its job. It's an aid in understanding these abstract concepts that we want to understand. They enhance our educational and computational approach, and the research is going on in this field, right? Okay, so this was, anybody wants to tell me anything, you can tell me. Come on. Okay, right? Fine. Now let's go. Now let's go with formalism. So what we have the spin. Okay, we have spin angular momentum. You have L equal to under root of L times L plus 1 H bar. You know where from it has come, you know everything about it, okay? And you can think of S as under root of S times S plus 1 H bar. So this S is the representative of spin angular momentum. If you rightly go back, you have a coupling, what we call as total angular momentum J. This J is the vector sum of L and S. Okay? This L is the result of orbital angular momentum of the electron that's associated with it. And this S is the result of the superposition of the spin angular momentum of the electrons. Right? Okay, fine. Can I move on? Okay? So, now, I will choose a state. Okay. When we have to write down the spin, we have to start with the amplitude of the spin. If you rightly remember, the solution of the Schrödinger's equation, it always comes in the form of amplitude. And you are always interested to write down the amplitude. And when you take the complex conjugate of that amplitude, you can calculate the probability. You can calculate the probability of having that particle or the probability of not having that particle. Now, if I choose a notation like this, what is it? First of all, it's a ket. It's an eigenket. Okay? Now, we understand what a ket can be depending on the way you are trying to solve your problem. Your ket can be a matrix. Okay? It can be a function. Okay? So it can be the things that are important here. So if I choose an arrow in the upward direction, and I assume that this arrow in the upward direction is the amplitude. It's the amplitude with the probability of having spin up. Okay? So if I choose this as spin up, and this is the probability of having spin down. And so this I choose as spin up. So this state, spin up, is a column matrix, 1 and 0. Right? And spin down is a column matrix, 0 and 1. Come on, copy it. Have you copied it? You should have copied it. Try to be fast. In the meantime, if anybody has a question, you can ask me. So what we have a spin-up state that is symbolized by an arrow, by an eigenket of an arrow in the upward direction. And then spin down is an arrow in the downward direction with this ket. And my spin up is a column matrix. So 1, 0 is a representative of spin up, and 0, 1 is a representative of spin down. Okay. Now, this spin it's a two-dimensional problem. If you remember, I talked about a spinor. What is it? It's a two-dimensional vector. And if I write down, this is spin up, ket. If I write down its component, what will be that? I will write down a symbol here as x. This x is representing what? It's the x component of spin up. And this we can write as a column of 1 by root 2 and 1 by root 2. Come on. Now, if you have spin up, it's a ket. When you transform a ket into bra, what happens to the matrix? It becomes a row matrix. And you take the complex conjugate of the row matrix. But we have numbers here. So for Ix, we have numbers. So if I write down the bra of spin up along x, this will be a row vector of 1 by root 2 and 1 by root 2. Now, the very first question to you. Why am I writing 1 by root 2? Yeah, come on. Why am I writing 1 by root 2? Come on, you can see it. This is 1 by root 2. Why? Psi is the solution of the Schrödinger equation. Psi 1 is the solution of the Schrödinger equation. Psi 2 is the solution of this Schrödinger equation. The superposition of psi, psi 1 and psi 2 is also the solution of the Schrödinger equation. And how do you handle that problem? Do you remember? You handle that problem by introducing By calculating the constant. You calculate that constant using normalization. Integral psi star psi dx, say for the sake of argument, in one dimension. This 1 by under root 2 is the result of that. It's a normalization. It comes from normalization. Otherwise, you are dealing with ones and zeros here. Getting my point? So, because I have to construct, see, I have to build Pauli's spin matrices. I have to build it. So, I am designing my mathematical formulas in that way. So, this is my spin up along x. Then, it's the cat, then you have its bra. Now, okay, spin down along x is a column vector of 1 by root 2 minus 1 by root 2. Right? So what will be its bra? That will be a row matrix of 1 by root 2 minus 1 by root 2. Okay? I'm writing down the things. I'm trying to formulate it. Right? And the things that you see there, they are the result of that normalization. This 1 by root 2. Now, if I write down something like this, if I write down an external product of spin up along x, spin up along x, minus spin down along x, spin down along x. I have written it down this way, okay? Spin up, the cat, the bra, the cat, the bra, and you subtract the two. Now what is spin up along x? It's a column matrix. What is it? It is 1 by root 2, 1 by root 2. This is the bra. I have written it wrong. Is it? No, this is cat. Okay, this is fine. So this is 1 by root 2, 1 by root 2 times the row 1 by root 2, 1 by root 2. Am I right? Then minus 1 by root 2 minus 1 by root 2. This is the column matrix 1 by root 2 minus 1 by root 2. Clear? Now let's have the matrix multiplication. Okay? So this will give me 1 by root 2 whole square, that's 1 by 2. Another term will be 1 by 2. Another term will be 1 by 2. Another term will be 1 by 2. Clear? Then you have minus. Come on, do the same thing here. You will have 1 by 2. Then you will have minus 1 by 2. Then you will have minus 1 by 2. And then you will have 1 by 2. Clear? Now what I have to do is to subtract the two matrices. I can do that. Come on. 1 by 2 minus 1 by 2 will give me what? It will give me 0. Come on. Then what I have? 1 by 2 minus will become plus. So this will give me 1. So here you will have 1. Here you will have 0. Here you will have 1. Come on, what's it? It is sigma x. Right? This is your component of the Pauli matrix, sigma x. So sigma x is what? It is 0, 1, 1, and 0. I think we will stop here. Huh? Okay? Anybody who wants to tell me anything? Any questions? Any questions? Okay.